Something from history. There was a group of Jewish soldiers who were surrounded by the Roman army, and so it's called the Josephus problem. It's based on something from history. There was a group of Jewish soldiers who were surrounded by the Roman army, and they didn't want to get captured, so they decided to come up with a system to avoid getting captured or suicide. So they'd sit in a circle, and the first man would kill the guy to the left of him. The next remaining living person would kill the next remaining living person with their sword, and they'd go around like this until there's only one person left, and then the last person would have to commit suicide, of course, rather than get captured. And the story, at least the story I was told, I'm not sure this is historically accurate, was that Josephus preferred capture to suicide, but he worried that if he said this, the other soldiers would turn on it. And so he wanted to figure out where should he sit within this circle in order to be the last man living. And then he would surrender rather than kill himself. That was the problem. It's a little tricky, so let's do a smaller example. Let's say there were 7 people. And so just to be clear, the way it works is person number 1 kills number 2. Person number 3 kills 4. 5 kills 6. But now things get a little harder to kind of see in advance, because 7, there is no 8, so 7 kills 1. 3 kills 5. 7 kills 3. So 7's the winner. 7's the last one left over. For Josephus, there were 41 people. He needed to figure out where to sit. The mathematical problem is if there were n people, where's the winning seat? So let's see how. How about we do 13? N is 13. This is the binary expansion, but using our new method, the 8 will be the 2 to the a, and the 5, which is the 4 plus 1, that'll be the L. And here's the thing that's going to happen with the L. I'm going to do 5 steps. So 1 kills 2. 3 kills 4, 5 kills 6, 7 kills 8, 9 kills 10. So now I've dropped L people, and it's number 11's turn. Now watch what happens. How many people are left? Well, what's left is a power of 2. And we know who wins in a power of 2. It's whoever starts.
The first killer. The
first killer. So now, if we go from here, I claim that 11's going to win. And just watch. It's going to be 11 kills 12, 13 kills 1. 3 kills 5, 7 kills 9, back to 11, and now there's only 4 people left. 11 kills 13, 3 kills 7, back to 11, 2 people, 11 wins. And so this is really the key to the final answer, which is if you've written your number as 2 to the a plus L, after L steps, whose ever turn it is going to win, because it's going to be their turn and there'll be a power of 2 left. And so the winning seat will be 2L plus 1. If you write it in this way, because that's whose turn it'll be after L steps. The theorem, or the claim, is that if you've written n in this way, so if n is 2 to the a plus L, where L is less than 2 to the a, it has to be strictly smaller. So in other words, 2 to the a is the biggest power that sat inside of n. Then the winning seat is going to be 2L plus 1. So we've already seen it was true here. Right? L was 5, and the winning seat was 11, which is 2 times 5 plus 1. And if you start going back through, you'll see the same thing for all the answers. We've already really illustrated the mechanism, which is after L steps, it's the turn of person 2L plus 1. And after L steps, there are a power of 2 number of people left. And when there's a power of 2 people, the first person who kills, that's who's going to be the winner.
Let's see if Brady has learned.
Yeah, all right. Let's do it.
This. I think I followed. Now, in the Josephus problem,
yep,
there was Josephus and 40 soldiers. So,
that's right. Oh, yeah, we got to go back and do that.
All right, so we've got 41 people.
So n is 41.
All right, so now, I think expressing that in the way you told me to, it's going to be 32 plus 9.
There you go. 32 plus 9.
So 2 lots of 9 plus 1 is 19.
There we go.
So we want to sit in position 19.
There you go. You want to sit in the 19th chair. So here we go. We're going to do n equals 41.
All right. Put them in the cave, waiting their fate.
Not a very good circle,
That's
but...
all right. Small them down.
I know. Should I redo this?
No, you're okay.
40, 41. Okay, there we are. So we got a little tight at the end.
Look
All
at
right.
that. This is a lesson about planning ahead, people.
Yeah. Okay, so let's do it. 1 kills 2, 5.
We're losing our even numbers.
Yep. Okay, now 41 kills 1. 3 kills 5. All And 19 kills 35, and there we go.
All right, I was right.
There we go, 19.
Yeah.
I'll note one other thing in this problem, which is kind of fun. So this formula I wrote can be interpreted in binary notation. When we wrote a number as a sum of powers of 2, this can be re-expressed in binary notation. So what was this? 32 plus 8 plus 1. So that's 2 to the 5th plus 2 cubed plus 2 to the 0. And binary notation, the digits correspond to the various powers of 2, and all the digits are 0 or 1. So 41 in binary notation would be 1 copy of 2 to the 5th, 0 of 2 to the 4th, 1 of 2 to the 3rd, 0, 2 squared, 0, 2 to the 1st, 1 to the... Here's a trick for the Josephus problem, which I won't justify, but it's super cool, and you can try it on your own. The way to find the winning solution, if this is n, the winning solution in binary is you take the leading digit and you put it at the end. So in other words, I claim that if I write 0, 1, so I take this part and then I add the first digit to the end, that number in binary code is, well, let's see, it's 2 to the 0 plus 2 to the 1 plus, I skipped 2 squared and I skipped 2 cubed, and I add 2 to the 4th. So it's 2 to the 4th plus 2 to the 1 plus 2 to the 0, which is 16 plus 2 plus 1, which is 19, which is exactly what the winning seat was. And so there's this super efficient way in binary code to jump straight from the number n to the winning number w of n. So if you're writing your numbers in binary code, the pattern would have been even more quickly apparent.
Amazing.
Isn't that cool?
Yeah.
Yeah. Isn't that cool?
Yeah. This video was filmed